Alright gang, here we go. Chem 2, Unit 2, end of Chapter 6, we're going to talk about electron configurations. Alright? So electron configurations is simply the way that electrons are arranged around the atom, okay? And specifically, it's the way they're arranged at the ground state. Now remember, electrons can jump between energy levels when they get energy, but specifically, since most of the time they're at their ground state, that's really what we care about. Alright, so this is how we write out electron configurations. They have three components. Okay, so the first one is the front number here, okay, and it tells us what energy level we're on, or the n quantum number. So the 4 right here tells us that we're talking about an electron that's on the 4th energy level, or n equals 4. The next guy tells us the type of orbital, right? So that's p, so it tells us that we have an L quantum number of 1, okay, so 4p, so we're on the p orbital of the 4th energy level, and then the last number tells us the number of electrons in that orbital. Okay, so specifically this element, whatever it is we're talking about, has 5 electrons in the 4p subshell. Okay, so remember, p can have 3 different orientations, so that means they can have a total of 6 electrons, because each orientation holds 2 electrons, one for a positive 1/2 spin and one for a negative 1/2 spin, positive and negative. All right, so these are called orbital diagrams. Okay, and each box represents one orbital. When we can have 2 electrons in there, we draw them in with half our arrows, and we either point them up or down to represent the m sub s, or the spin of that electron. All right, so a positive 1/2 points up, negative 1/2 points down. Okay, so this tells us that for lithium, we have 2 electrons in the 1s orbital and 1 electron in the 2s orbital. Okay, and notice, so we put, one going up, one going down. Okay, remember we talked about how Pauli exclusion principle tells us that we can't have more than one electron with all the same quantum numbers. So if we put 2 electrons with both pointing up in 1s, that would mean they both have the same m sub s number, and the same n, and the same l, and the same m sub l. That's a problem. Okay? Alright. So this devolves into what we call Hund's rule. So there's 2 important rules. We got the Pauli exclusion principle saying no 2 electrons can have the same set of quantum numbers, and then Hund's rule says that when you're filling orbitals on the same electron level, that you always fill it from lowest to highest. Okay, and you always fill them so that they maximize the number of spin elements. Okay, so here we've got lithium, so you've got 2 electrons in here, and you've got 1 pointing up. Okay, beryllium is the very next element. You got 2 in the 1s and 2 in the 2p. Okay, notice how the very next electron, there's only 1 electron difference between lithium and beryllium, and it gets 1 electron that's going to be pointing down next to the one that was pointing up. Boron is number 5, so it's got 1 more electron than beryllium, so we put it in the very next box because we are always filling from the lowest to the highest. All right, and it's pointing up. Okay, and then carbon has 1 more electron. Okay, now notice how we're going to split them up, and we're going to put 1 up arrow in each box first, and then start filling them up with down arrows. Okay, so here's carbon. So the new electron that boron didn't have goes right here in this box, and then nitrogen has the next one right here. It goes up 1 more, so we get an electron right here, and then we're going to skip 3 more, and so you can imagine between nitrogen and neon, you get electrons that are filling them in like this, and so they're going to go 1, 2, 3, and just add and so on and so forth. Okay, and then sodium, we jump up to the 3s, and we get that 1 electron right there. Okay, so those are the orbital diagrams. The orbital diagrams show us how the electrons are put into all these different orbitals, and then these guys here, the electron configurations, this is the written out way we keep track of where our electrons are. Okay, so one thing to keep track of, to help you keep on track, is when you take these exponent numbers, remember these numbers tell us how many electrons are in each orbital. If we add all of those guys up, it should equal the total number of electrons in that element. Okay, so lithium is 3 electrons, and we take 2 plus 1, sure enough it's 3. So that's one way to go double check yourself. Let's do another one. What if we do neon? 2 plus 2 is 4 plus 6 is 10. Sure enough, we've got 10 electrons. So that's one way to keep track of yourself. So if you have the orbital diagram, then all you have to do to write out the electron configuration is just write out what's going on. Well, we've got, we're in the 1s, we'll write 1s, and then there's 2 electrons in there, so we'll put a 2 up here. And then we're in the 2s, and then so we're 2s, and there's 2 of them in there, so we'll put a 2 up here. And then we're in the 2p, so we write 2p, and there's 6 electrons, 2, 4, 6, and we put a 6 up there. All right, that's how you go about writing electron configurations. All right, now once you get farther and farther down on the periodic table, you can see that it get pretty monotonous. Like by the time we got to sodium, we're just writing 1s2, 2s2, 2p6, like, and it's always going to be the same. The next one over is going to be 1s2, 2s2, 2p6, and so on and so forth. And so everything, as you move up, everything is going to stay the same from the row that was above it. All right, so we come up with what's called the condensed electron configuration, and this allows us just to worry about the outermost shell, or the valence electrons. All right, so for lithium, instead of writing out 1s2, we can put a bracket helium, because we know that lithium's electron configuration is going to be exactly like what helium's was, plus a 2s1. Okay, the next one down, straight down from sodium is, or from lithium, is sodium. Okay, sodium's electron configuration, notice from right here, is exactly the same as neon's, right? They're both 1s2, 2s2, 2p6, but the sodium has the 3s1 built on the end, so it makes life a little bit, so the only difference between those two is this 3s1, so we put a bracket neon, pretty much implying that the core electrons, or the ones that are underneath the valence electrons, are just exactly like neons, but then we've got the 3s1 on top. The reason this is important is twofold. Number one, it's way easier because we just have to write out what the, bracket noble gas, that's easy. And then number two, it allows us to focus on the valence electrons. And the valence electrons are where the magic happens. That's where bonding occurs, that's where it's going to lose or gain electrons, so on and so forth. So that's why keeping track of the valence electrons is so important. All right. Now, when you get to transition metals, life gets slightly more complicated, all right? And that's because, remember before in the previous video, we looked at these energy levels for these orbitals, and we saw that generally S, P, D, and F, it kind of goes in that order. But they're all for those same values. So this would be a 1s, and so at a 2s level, 2s is always lower in energy than a 2p. But once we get higher, the 4s is actually at a lower energy level than 3d. Notice how we get 4s. So we got 3s, 3p, then we jump to 4s, and then the 3d, and then a 4p. So life gets more complicated. The d orbitals occur in the transition metal area of the periodic table, and you should remember that the transition metal area of the periodic table is kind of in this area right here. Those are the transition metals. All right, so right there. So once we get there, that's the D block. And so life gets more complicated. We have to worry about, all right, the 4s is going to get filled before the 3D because it's in a lower energy level. And then when you move down to the next row, then you're going to fill the 5s before you fill the 4D, and so on and so forth. And life gets way fun, and we have to think about all these things. All right, so then... excuse me. So those are the transition metals. Then we have the lanthanide and actinides, guys. So if we look at our periodic table, all right, if you look at the vast majority of periodic tables have it look like this, more or less. I'm not the best artist in the world. And then we've got another set of 2 rows down here. Okay, and they're kind of split up. These rows here, the lanthanides and the actinides, fit in right here. Okay, so if we were gonna, there's a picture of it here. If we were gonna put in the lanthanide and actinides inside the periodic table, it would make our periodic table way longer. So this F block is usually written down below. Okay, so we usually get the S, the D's, and then the P's. All right, and then the F is kind of off. But if we were gonna write it all out, it would look like this. Okay, so the lanthanide elements are these guys over here. All right, atomic numbers 57 to 70, and the actinides are these guys here, and they include uranium, plutonium, and all these really fun elements down there. Okay, and these all fill f orbitals. All right, so these bottom blocks are the f orbitals, and they're even lower in energy. So you're going to fill 4f after 5 or after 6s. So life gets pretty exciting there. All right, so anyway, so this is like, if there's nothing else you take away from anything else, this is what you want to look at in your book when you're helping yourself write out periodic table or the electron configurations. All right, so you go from 1s 2. So if you're looking at helium, we're at like 1s2, and so we're done. Okay, and then, but if you're down here on an F block, you can be like, all right, I got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5b6, 6s2, and then 4f1, 2, 3, 4, 5, 6. All right? We'll do some practice. It'll be okay. All right? So, the periodic table is what you're simply going to look at for like the vast majority of elements. Once you get farther down, life gets more exciting. Okay, obviously you have to start thinking about where does that F block squeeze into the periodic table. Okay, but there are some exceptions. All right, and the biggest anomalies occur in the middle of the period, or in the transition metals, and this is where we have a place where there are enough electrons to half fill both the s and the d orbitals in a given row. All right, so the big example of this is chromium. Okay, right here. So if we were going to write out chromium, we would know, well, it'd be just like argon. So we'll just be like, all right, so there's our argon, and then it would be, if we were going to write it out like normal, it would be 1s, 2s, 3s, 4s would be 4s, 2, and then 1, 2, 3, 4, and then 3d4. Now, the trick is it doesn't actually follow that pattern, because if we took one of these electrons here and put it with this, we would end up with this guy, argon 4s1, 3d5. Okay, and if we were going to draw out the orbital diagrams for these, okay, so here's our 4s, so we got one electron here, and then we got 3d, and we'd have 1, 2, 3, 4, so 1, 2, 3, 4, 5, and so we'd get 1, 2, 3, 4, 5. We get something like this. All right. Now, because 4s and 3d are so similar in energy levels, like 4s is lower, but it's pretty darn close to 3d. It's actually more stable for the electron to be split out and have two half-filled orbitals instead of one full 4s and then a 4/5 full 3d. All right. So our chromium specifically has this as its electron configuration, as opposed to this. And this is the big exception that I want you to know. Okay, know this. And you should be able to explain why this is. Okay, and it's because the 4s and 3d orbitals are very close in energy. They also occur in the F block atoms and the d orbitals as you move farther down, so the guys underneath chromium. So it happens again with molybdenum and tungsten and seaborgium. All right, and then it happens again at number 6 of the lanthanides. 1, 2, 3, 4, 5, 6. This guy here, so on and so forth. But chromium is like the big example of like, because chromium occurs a lot. It's only element 24. There's a lot of chromium bouncing around. Okay, so that's the big one I want you to pay attention to. All right. Let's see. Let's do some of these. So how many how many of the elements in the second row of the periodic table will have at least one unpaired electron in their configurations? All right. So if we bounce back to, well, I'll just pull up a periodic table right here on a browser. So if we're looking at, so look at your periodic table here. All right. So maybe I'll just drag this guy over here. So if we're looking for lithium through neon, lithium through neon. All right, lithium through neon. So we've got these guys here. How many of them are going to have an unpaired? Well, lithium's going to have an unpaired because it's going to be a 2s1. Beryllium won't have any unpaired. Boron will, because it'll have 1 in the p, and then carbon will, because it'll have the 2 p's will be by themselves, and so will nitrogen. Then once we start going here, they're going to start pairing up. The oxygen electron will be paired up with the one from boron, fluorine with carbon, and neon with nitrogen. All right. So that's kind of how you think about these ones here. Okay. All right. So let's write out the electron configuration for silicon, element 14 in its ground state. So let's see. So silicon's element 14. So we have 1s2, 2s2. Remember, when we add all these guys up, they should add up to 14. If we look at the periodic table again, right here. All right, so silicon's 14, so we know for sure we're going to fill up all the way up to 3s2, no problem. So 2p6 is going to be filled, all right, and 3s2 is going to be filled. So right now we're at 12, so we got 2 more electrons. So these guys right here, aluminum and silicon. So we'll have a 3p2, Okay, so that's the ground state, and both these guys, so if we draw out the orbital diagram for these, all right, so there's our p, this will be our 3p, and it'll be split into thirds, and we'll have these two electrons here, and we'll fill it, and we won't pair them up because of Hund's rule. So it has two unpaired electrons for silicon, the ground state of a silicon, right? So then we can also, there's patterns within the groups for the electrons, all right? So a certain atom has ns2np6, so that, remember, that's those n's are our energy levels, either 1, 2, 3, 4, or essentially what period we're on the periodic table. Okay, and we need to identify, well, which of the following elements would these be? So beryllium, silicon, iodine, krypton, or rubidium. So remember, so we're looking for places that are ns2, np6. Well, np6 only happens here, right? So neon, argon, krypton, xenon, radon. Okay, so the only one this works for is krypton. All these other guys are going to have other things outside after its outermost shell. Okay. All right, how about, let's do one more. So characterized by ns2, np2. So let's see, ns2, so these are completely filled, and then np2, so it's got to be these guys here, carbon, silicon, germanium, etc. These guys will all be that as their outermost occupied shell. All right, a couple more practice problems. So we've got a certain element that's the noble gas. They're not telling us what the noble gas is. Those boogers. All right, 5s2, 4d10, 5p4. So we're going to look at our periodic table. So 5s2, that's these guys. And then we jump to 4d10. So all those are filled all the way to cadmium. All right, and then 5p4. So 1, 2, 3, 4. So it's got to be tellurium right here. So it's got to be Te. All right. There you go. And it was one of the options. Thank goodness. All right, use the periodic table to write the condensed configuration for cobalt and indium. So cobalt is element 27. Let's find it on the periodic table. Cobalt's right here. So we know, so it said condensed, so that means we can use argon. So I'll be like, all right, so I'll make a little note here. So cobalt would be argon, all right, and then, so now we're on 4s2, and then 1, 2, 3, 4, 5, 6, 7, and then 3d7, all right? So that's cobalt, that's easy. And then indium, right here, 49. All right, so condensed would be krypton. So we'll say indium, Kr for krypton. And so it's on this row, so that means it starts with a 5s2. And this whole thing's filled up. So remember, they're always going to be one delayed, so this is going to be our 4d10. All right, so all these guys are good. 4d10, this is filled, and then that gets and then we'll have one more for a 5p1. So there's our condensed periodic table, or condensed electron notation for indium. All right. Here's a link that I included. You could test these out. There's lots of great practice out there. Like, honestly, you could hop on Google and just type in electron configuration practice. You'll probably find like a bazillion practice problems. But anyway, so that concludes Chapter 6. Unit 2 is a dense one, right? We've combined, we're doing the bare bones of 3 chapters in our book. We're doing the bare bones of Chapter 2, bare bones of Chapter 6, and bare bones of Chapter 7. So we're 2/3 of the way there. Keep on keeping on. You can do it. Let me know if you have problems or practice, and I'll see you later.